Okay, welcome along. Bit of a two-parter. Going to start off kind of working out what you know about energy and gravitational fields at the moment. Going to establish a couple of new bits of terminology, in particular the term potential and equipotential. And then we're going to pop out in the garden, and despite the wind and the rain and the noise from the builders, we're going to have a go at just trying to explain these concepts in terms of work done. I think we'll do a separate video to kind of do the maths, just make sure you've got your head around the ideas. So what do we know currently about potential and potential energy? So I'm going to kind of imagine that we're in a building. Here we are. Here's a table. And then we're going to kind of imagine moving an object from the floor onto the table. And as you know, we can calculate the work done on the object as we move it from there to there by doing force mg times distance h. So assuming the object's got mass m and we move it distance h, that's the increase in potential energy. One of the limitations here, which we've probably not talked about before, is that this only applies, of course, when g is constant. And so whilst that works fine for our classroom, if you were sending a rocket from the Earth to the moon, g is going to vary over that trip and mgh is not going to apply. So that's the kind of first problem that we're going to try and tackle, or first issue that I'm going to raise. It can be useful to think about this tabletop as being a place where all objects placed on the same tabletop have the same distance h above the floor, and that tells us something universal about the amount of energy any object moving from the floor onto the table will gain. So we're going to have a look at that. It turns out to be very useful, rather than just dealing with potential energy, that's the energy of the object by virtue of its position in the room or the gravitational field. It can be useful to talk about potential. Potential is the amount of energy per kilogram. So let's just remind ourselves, we had field strength, which was the amount of force per kilogram. Now we've got potential, which is the amount of energy per kilogram. Perhaps should get in here that this is a vector quantity, because force is a vector, it has magnitude and direction. So field strength is a vector, has magnitude and direction. This is a scalar, it only has magnitude. So potential energy is a scalar and potential is a scalar. So everything on the table relative to everything on the floor has the same potential energy, so it has the same potential. So if we take an object, move it onto the table, the increase in potential per kilogram is mgh over m, so it's equal to gh. Now mathematically that's not something we're going to use, but that then represents gh is the difference in energy per kilogram between the floor, and the difference in potential between the floor and the table can be written delta V is G, and I suppose you better put delta H because it's the increase in height between the two. The work that we need to do to move from the floor to the table is the mass of the object multiplied by the difference in potential, because that's the number of joules per kilogram difference, and that's the number of kilograms that we're moving. So when you multiply them together, you get the increase in energy in joules. So concept one, we need to think about potential being the amount of energy per kilogram. Concept two, we're going to think about within our room equipotentials. So all lines drawn parallel to the surface of the planet and at right angles to the field, I'll put the field in at the moment, are equipotentials. So let's just write that word. So they're lines of equal potential, equi meaning equal. So everything along that line, you move an object along that line, it'll have always the same potential energy, and the energy per kilogram, the potential is the same everywhere along that line. Those equipotentials are always drawn perpendicular to the field line. So the field, as we drew it before, looks like this. They always, equipotentials and field lines always meet at right angles. We only do work moving an object in a field, change its potential energy, if we move along a field line. So if we move up, we increase its potential energy. We move down, we decrease its potential energy. But if we move parallel to it, then no work is done. If you remember, work done is force times distance, but only if these are parallel. Or you might have seen it as work is Fs cos theta. Cos of 90 is 0, so no work that is done when the force and the displacement are perpendicular to each other. Now finally, and my diagram's got sufficiently messy now, I'm going to draw you another one. Really, when we're dealing with MGH, we're always dealing with the difference in potential energy between two locations. And it would be really handy if we could have a standardized location that had 0 potential energy. But it doesn't really seem to matter where you are. There's no particularly convenient answer. You might say, can we make the floor of the room 0 potential energy? Well, not really, because if you went down to the floor below or to the basement or whatever, you would have less energy, wouldn't it? So you might say, well, John, there's planet Earth. Well, you can't go lower than the centre of planet Earth. So maybe the centre of the Earth should be the point of 0 potential energy. But as they say, there's always a bigger fish. Well, but, you know, I haven't drawn it to scale, but what about Jupiter? The potential energy at the centre of Jupiter for the same object is considerably less than it is on Earth. And you can just go up and up and up, and you end up in a kind of a mess. There's no place where you have the lowest possible potential energy. There is, of course, a solution. If this is planet Earth, the place we treat as 0 potential energy or 0 potential is far, far away. Okay, more technically, it's an infinite distance from all mass. So we get a cost benefit here. The benefit is it doesn't matter where you start, whether you started from Earth or Jupiter or, you know, a quasar and it's, you know, huge supermassive black hole. If you move from the quasar to Jupiter to far, far away, once we get there, all these people can agree that's 0 energy there. So that's good. There is a cost, and this is the cost. If this is where you have the max possible amount of energy, isn't it? So the cost is that when you go back to your home planet, the potential will be a negative number, because if the maximum value is 0, all other values are less than 0, all numbers less than 0 are negative. So all potentials are negative numbers. So on the surface of the Earth, the potential is minus 63 megajoules per kilogram. So that means we would need 63 million joules to move 1 kilogram from the surface of the Earth out to far, far away. And as I say, I'll now do a bit of skipping around the garden just to try and help you visualise that. Hi, welcome along. I'm going to do a little bit of an explanation about increasing and decreasing potential energy. Got a table to represent our equipotential surface. Ground is another equipotential surface. Nice hefty rock. So it's it's on the ground, it's got less potential energy. I know you know this, but when we kind of start thinking about it with planets, it gets a bit more awkward. So I'm going to do work, increasing its energy, more and more and more energy. When it gets up to there, it's got more potential energy. It's at a higher potential. When I let it go back, it's pulling me, it does work on me, it lowers its energy to where it wants to be. It wants to be in a lower energy state, and when it gets down there, we've got a lower potential energy because it's done work on that. All can be done by MGH because what we're dealing with here is a uniform gravitational field. Let's see how that varies when we start moving further away from the planet. So, second part of our little explanation of potential energy. How things are going to be different? Well, there's a couple of things that are different here. First of all, here's our planet as represented by this nearly spherical and planet-shaped barbecue. Our rock's just the same. One of the things that's different is we're going to have a universal zero. So when I go over here, we're going to call this far, far away. The example, rather, you called it infinity, an infinite distance from all mass. But this is the point where this has zero potential energy. This is the point out here where potential is zero. We can't use MGH anymore because as we move between here and here, G is varying. Okay, the further we get away from our planet, the weaker the gravity is. But the key thing is the work done to work is the same. I'm pulling this rock away from there, I'm giving it more and more energy, I'm doing more and more work on it, and therefore I'm increasing the rock's potential energy. It always wants to shoot back here and reduce its energy. It wants to do work on me and lower its energy. I have to do work on it. And as I carry it all the way here, doing more and more work. Now it's getting easier because the gravitational field strength is weaker. I'll get over here, I'll get to an infinite distance, I'll get to far, far away, and now it's got zero potential energy. You're out, it's zero. As we go back, it wants to go back, it's doing, the field is doing work on it, we're lowering its energy. Its energy is getting less and less than zero. Right down here on planet Earth, it's got an energy of minus 63 million joules per kilogram. That means I need to supply 63 million joules for each kilogram to move it out there to far, far away where it'll have zero potential energy.